before is what? Where we have the flange is 0.392 plus by twice the width is 0.2. Okay, so the twice down here is left and right web. Okay, so 0.2 width, and then the depth is 1.5, and the centroid is 1.5 divided by 2. So this is equal to 0.392 plus by 0.75 times 1.5 divided by 2 times 1.5 times 0.2 times 2 plus by 0.45. Okay, so plus by, wait, 2. Hold on, my thickness is wrong, 0.3. Okay, it's not 0.2. So 1.5 by 2 times 1.5 times 0.3 times 2 is 0.675. So 0.392 plus 0.675 equals 0.392 by 0.675, 1.067 inches cube. Okay, so your shear at point C is equal to V over I. Q is equal to 1.067, right, divide by thickness, which is 0.3. And then you have to consider 2 over here, because why? Because you have 2Q, and 2Q is because it is a box beam. Okay, so I will write over on the previous slide also, the 2Q is over here because 2Q, because it's a what? Box beam. Okay, so that's our box beam. So from here, 1.067 divided by 0.3 divided by 2, 1.67, 1.067 divided by 0.3 divided by 2. So I get 1067 over by 600 V over I, or we get 1.778. So what you see over here, that the shear at point C is definitely bigger than the shear at point A, point B. Okay, so now I'll do something. I'll do something else. Okay, you have seen this briefly last week. I'm going to do it again. Now, what if we're going to do this analysis from the bottom? Okay, so if we start from the bottom, same thing. Oi, the image did not come. Unbelievable. Okay, so what if now, if we're going to carry out our analysis from the bottom, and why I'm doing this, you don't need to do this for your exam. I'm doing this to I want you to gain confidence. Okay, I want you to gain confidence. So now, what if now, right, we're going to do the analysis from the bottom. Okay, we're going to do our analysis. So if you were to sketch our shear flow, right, our shear flow will look like this. Right. So now we want to find point C over here. And the end point, right? The end point, this is our end point. The shear flow only go through what? One end point, right? And we know if we analyze from the bottom, right? If we analyze from the bottom, it's going to be a what? A white flange. Okay, so so from bottom, so to find the shear at point C from the bottom, the analysis is now it becomes a white flange. So if white flange, you only have what? one Q. You don't have two Q now. Okay, you only have one Q. If it's a box flange. Anyone, any questions so far? Are we okay?
Eugene, good question.
Yep.
What defines like a wide flange? Because like when I look at the bottom half, it doesn't necessarily look like an I-beam to me. So like, what makes it a wide flange in the first place?
Good question. As long as the end point or the start point is not a common point. Does that
Okay, so
make
it has
sense?
to be both start and both end, right?
Yeah, yeah. So if you're a good one, okay. So if you look at box beam, it starts at the same point, two arrow flows out, right? And then it ends at the same point. You see that, right?
Right.
Right? You get that, right?
Yep.
Whereas for the white flange, it starts from different point and it ends at different point.
Okay, gotcha.
Right? Right? So that's why I realized that, hey, see, I'm upgrading the way I teach. It's not just the initiation, it's also the end. Okay, so that's where we classify it as a white flange. Okay, good question. Anyone else? Are you all clear or no? The rest of you, no comment. Are you okay? I hope you are okay. Right. So point C is from the bottom and the analysis is white flange. So when that's the case, okay, the area is this area to consider only. The one that I'm shading in green. Maybe green is not a great color. Okay, so I'm going to, yeah, you only need to do this. Okay. Okay. Remember what I told you guys, right? This topic, we only have two formulas, yes or no? Right? Q equal to V over I multiplied by Q, and then the shear stress is VQ over IT. But it's the analysis. When to apply what? Okay, that is the confusing part. Okay. Okay, right. So now we're going to find again the shear at point C is equal to VQ over IT. So we know, like, now we know that the thickness now is equal to 0.3 inches. All right, Q, we only have one Q to consider. So the shear, the first moment of area at point C, so the flange, so I take the width to be 0.7 multiplied by 0.2. So in fact, we have this 1.5 minus by 0.2 divided by 2 minus, plus by 1.5. The width is, the width is 0.3. Let me check the width. Yep, the width is 0.3. The depth is 1.5. And then this is 1.5 divided by 2. Okay. So when you get this, so 1.5 minus by 0.1 times 0.2 times 0.7 is 0.196 plus by 1.5 divided by 2 times 1.5 times 0.3, 0.3375. So this will be equal to 0.196 plus 0.3375 is a plus 3375 is equal to 0.5335. And this is inches to the cube. So when we have that, we find the shear point C is equal to V over I, still the same. Q is 0.5335. I is equal to 0.3. 0.3 or 0.2? 0.3. And down here, you don't need to multiply. So I'm going to put 1 down. You only need to put 1 because Q and the analysis is a what? White flange. So from here, so 0.5335 divided by 0.3. So this is equal to 1067 over 600 V over I, or is equal to 1.778 1.7783 V over I. Okay, like what I was telling you guys, right? We have seen this number before, right? So this is from the bottom right? We took this from the bottom, right? And then we took this from the top, right? The answer is the same. I want you to, if it's done correctly, okay? If it's done correctly, it's correct. If it's done wrongly, it can be wrong. Okay, but I want you to have the confidence now that whether you take from the top or we take from the bottom, the answer will be the same. And the critical part is again the first moment of area. Okay, again the most critical part is the what? Is our first moment of area. So from now, from here, we realize that the shear stress at point C is greater than the shear stress at point A and the shear stress at point B. So therefore, the shear stress at point C is equal to tau max. Okay, the shear stress at point C is equal to our tau max. So from here, we know that shear stress at point C, we know the maximum shearing stress allowable is 10 times 10 to the power 3 psi. So this will be equal to V over I multiplied by 1067 divided by 600. So the V over I ratio, right, we know this V over I ratio is 10 to the power 3 times 600 divided by 1067 is equal to 5623, okay, 5623 or 5.623 times 10 to the power 3 and Newton over meter to the power 4. Okay, so that's how. So like what I mentioned, regardless of the point, V over I ratio is always what? Constant. So therefore, we know that the shear stress at point A is equal to the shear stress at point B, and this is equal to V over I multiplied by 0.98. Okay, so we have that relationship, right? So the one of the rules that we have generated is V over I is constant regardless of any point of analysis. Okay, so this will be equal to 5.623 times 10 to the power 3 multiplied by 0.98. So this is equal to 0.98 times 5.623 power 3. So it's equal to 0.98 multiplied by 5510 5.510 times by 10 to the power 3 Newton per meter square. Okay, let me do it again. 0.98 multiplied by 0.623 power 3 5.510 to the power 3 times 600. Okay, so that's the right answer. Any questions so far? Anyone? Yes.
Is it a coincidence that tau A and tau B are the same, or is it like why are they the same value?
Yeah, it's just a coincidence for this case.
Oh, okay.
Okay, it's just a coincidence for this case. Okay. If you look at it geometrically, it makes sense also. Why I say that? If you look at it, if you look at it geometrically, right? If you look at here, good observation, okay? If you look over here, wait, let me see before I make that statement. Yeah, so from here to here, if you just take this area over here, right? Right, you just take the arrow from where initiate, right? This is also 0.7. So this is also 0.7, and then the thickness is also 0.2. Okay, for this case, not always case, just a coincidence. Right, that's clear now, yes?
Yeah.
Okay, thank you. So the next one, yeah,
Dean,
yes.
why is it that just because tau at C is greater than tau at A and tau at B, that means it's the maximum? I don't think it's a valid proof that it's the maximum. I understand in theory it should be. We said we were going to prove that it was the maximum, but I don't think we did that.
Yeah, it's the maximum because that is the maximum area that we can consider. Remember, I wrote this statement, right? At point C, right, at point C, Q at point C is at its what? Q max. There's no other way that the area can get any bigger.
Right. Thank you.